record, and then I probably have to send it to you guys after, but we'll do that. Or maybe it goes in the cloud. Either way. So let me share my screen. Can you guys see this?
Yes.
Very good. I'll just move it a bit. Okay, so I can also see you guys, and I want to get the chat window open just in case I need it. Sorry, let me just put it right here so I can see. Good. All right. Yeah, so I want to tell you a little bit today about the mysteries of particle physics. And one interesting thing about particle physics is that it really describes the universe. So some of the things I'm going to talk about is also related to how the universe works and where we come from. And so what I thought I'd start with is a video that you can find. It's a TEDx video. Maybe some of you have seen it, maybe not. I'll just put the link in the chat here. And as I said, feel free to just watch it on your own. But let's just see if you can see this. If not, watch it on your own. This is about 5 minutes long. And it sort of introduces many other things that I will talk about, but I thought it's just really nice. It has nice animations and so on. So let's just watch this. As I said, if your internet connection is bad, just click on it yourself and watch it. Oh, hold on. Give me 1 second. I should share my audio. Let me reshare my screen for a second. Stop share, because I think if I share, I should share the sound. Otherwise, that won't work. Okay. Here it is. Can you guys see the screen again?
Yes.
Okay. So with a little bit of luck, you now also hear my sound.
If you were to take any everyday object, say a coffee cup, and break it in half, then in half again, and keep carrying on, where would you end up? Could you keep on going forever? Or would you find a set of indivisible building blocks out of which everything is made? Physicists have found the latter, that matter is made of fundamental particles, the smallest things in the universe. Particles interact with each other according to a theory called the Standard Model. The Standard Model is a remarkably elegant encapsulation of the strange quantum world of indivisible, infinitely small particles. It also covers the forces that govern how particles move, interact, and bind together to give shape to the world around us. So how does it work? Zooming in on the fragments of the cup, we see molecules made of atoms bound up together. A molecule is the smallest unit of any chemical compound. An atom is the smallest unit of any element in the periodic table. But the atom is not the smallest unit of matter. Experiments found that each atom has a tiny, dense nucleus surrounded by a cloud of even tinier electrons. The electron is, as far as we know, one of the fundamental, indivisible building blocks of the universe. It was the first Standard Model particle ever discovered. Electrons are bound to an atom's nucleus by electromagnetism. They attract each other by exchanging particles called photons, which are quanta of light that carry the electromagnetic force, one of the fundamental forces of the Standard Model. The nucleus has more secrets to reveal, as it contains protons and neutrons. Though once thought to be fundamental particles on their own, in 1968 physicists found that protons and neutrons are actually made of quarks, which are indivisible. A proton contains 2 up quarks and 1 down quark. A neutron contains 2 down quarks and 1 up. The nucleus is held together by the strong force, another fundamental force of the Standard Model. Just as photons carry the electromagnetic force, particles called gluons carry the strong force. Electrons, together with up and down quarks, seem to be all we need to build atoms and therefore describe normal matter. However, high-energy experiments reveal that there are actually 6 quarks: down and up, strange and charm, and bottom and top. And they come in a wide range of masses. The same was found for electrons, which have heavier siblings called the muon and the tau. Why are there 3 and only 3 different versions of each of these particles? This remains a mystery. These heavy particles are only produced for very brief moments in high-energy collisions and are not seen in everyday life. This is because they decay very quickly into the lighter particles. Such decays involve the exchange of force-carrying particles called the W and Z, which, unlike the photon, have mass. They carry the weak force, the final force of the Standard Model. This same force allows protons and neutrons to transform into each other, a vital part of the fusion interactions that drive the Sun. To observe the W and Z directly, we needed the high-energy collisions provided by particle accelerators. There's another kind of Standard Model particle called neutrinos. These only interact with other particles through the weak force. Trillions of neutrinos, many generated by the Sun, fly through us every second. Measurements of weak interactions found that there are different kinds of neutrinos associated with the electron, muon, and tau. All these particles also have antimatter versions, which have the opposite charge but are otherwise identical. Matter and antimatter particles are produced in pairs in high-energy collisions, and they annihilate each other when they meet. The final particle of the Standard Model is the Higgs boson, a quantum ripple in the background energy field of the universe. Interacting with this field is how all the fundamental matter particles acquire mass, according to the Standard Model. The ATLAS experiment on the Large Hadron Collider is studying the Standard Model in depth. By taking precise measurements of the particles and forces that make up the universe, ATLAS physicists can look for answers to mysteries not explained by the Standard Model. For example, how does gravity fit in? What is the real relationship between force carriers and matter particles? How can we describe dark matter, which makes up most of the mass in the universe but remains unaccounted for? While the Standard Model provides a beautiful explanation for the world around us, there is still a universe's worth of mysteries left to explore. Ready to start exploring? Dive right back into the perplexities of the universe with these two lessons.
All right, so this is how I wanted to start off. Were most of you able to see the video? Did it work? Okay, excellent. Good, so there were lots of things in this video, and most of my talk now I want to actually go into a little bit detail into the many things that were talked about in this video. So we heard about different forces. We heard about quarks and leptons. We heard about something like the Higgs particle and dark matter. And so I want to, in this talk, go over all these different things. So one of the things that was talked about were the four fundamental forces. So we believe, or all forces that we know of in the universe that exists right now are four forces that exist. There's gravity, which we all know about, right? That's what binds us to the Earth. There's electromagnetism, which is sort of what light is, and electric and magnetic forces. There's a strong force that was already said in the video is what holds the nuclei together. And then there's a weak force that is responsible sort of for particles to decay, and is also responsible for the fusion processes that actually fuel the sun. That's why the sun is hot and puts so much light. So the first question I have for you guys, and just use the chat window, just type in, which of these two forces do you think is the strongest force? So just chat, just type it into the chat, and I'll look at the chat. I'm gonna wait till I want to have several. Okay, so most people say strong force. I hear see not gravity. Very good. So let's actually, and so that was the strong force. That was the strongest. What do you think is the weakest force? Oh, you guys are good. Most people say there's lots of gravity. A few of them say weak force. A few of you said weak force. So let's actually look at this. So this is an first interesting question. So let's assume for a second we call the strong force, 1. So let's measure things in units of the strong force. Oh, sorry. Before I go there, I wanted to give you this thing because, many people, you ask the same question to elementary school kids, and almost everybody thinks gravity is the strongest force because, after all, come on, it holds us to the Earth, right? We don't fly off. And so on. And so here's always this argument that I give. So imagine we take in magnets and we pick up a paper clip. We pull it, above the table. So clearly the magnet is able to counteract gravity by pulling the paper clip up. where the paperclip wants to fall down. And now you think about this a little bit. So I have this magnet that I can hold in my hand that's pulling on one end. Now what's pulling on the other end, right? Well, it's actually the entire Earth that's pulling on the other end. The Earth is a lot bigger than that magnet. Okay, so most of you actually have this right, and this is not a test, of course, it doesn't really matter. So the really interesting thing is gravity is the weakest of all forces. So you might actually ask, how much weaker? How weak and how strong and weak are those interactions relative to one another? So I should mention the standard model is describing 3 of those 4 forces and is not describing gravity. There are people who are trying to understand how you can combine gravity and the other forces together, but that is not something I will talk about today in this talk. So let's look at the forces, the strength of these forces. So if the strong force, let's call this strength 1. Then what you'll find is electromagnetism is about 1% of that. So it's about 100 times weaker than the strong force. Now the weak force is pretty weak. That's why we call it the weak force. It's the weakest force of the standard model. It's 10 to the minus 6. And you guys, some of you probably know what I mean by that notation 10 to the minus 6, but let's just be totally clear. When I say 10 to the minus 6, I mean it's 0.0000001. So 6 zeros and then a 1. Okay, that's 10 to the minus 6 means. So how weak is gravity on the scale? 10 to the minus 8. I already told you it's weaker. Well, it's actually 10 to the minus 38. So it's 0 points, then 38 zeros, and then a 1. So in other words, it's like 32 orders of magnitude smaller than the weak force. So it's incredibly weak. Okay? And so I will just not talk about gravity for the rest of this talk. I'll focus on the 3 forces of the standard model and tell you about those. So this is also a figure that you saw in the talk. By the way, I should mention, if you have any questions, just unmute yourself, interrupt. You can also raise your hand. I just have to figure out, maybe if one of you guys can monitor, I don't know where to see to raise your hand right now, or just type something into chat if you want, but maybe one of you guys can monitor. Somebody has a question, I don't see it, just interrupt me. Good. Yes. Very good. And okay, so you saw this figure already, and it talked about some of these particles. So let's go over these particles a little bit. So what you see, let me actually get my annotate. Oops, sorry. Let me get my spotlight here. So what you see out here, these particles, those are what we call fermions. These are matter particles. Up here in red are the quarks. And down here in green are what we call leptons. And we'll go about this a little bit more in a second. These particles in blue here are these force carriers. Those are the particles that mediate the 3 forces. And I'll tell you more about this in a second. And then there's a Higgs particle in the middle, which we will talk about, which has a pretty special a role in the standard model. So let's try to look at this. And so electromagnetism, that you probably know, is mediated by force, or the force is mediated by the photon. So the photon is the force carrier of electromagnetism, and essentially the photon couples to charged particles. So the force is then mediated. Imagine I have an electron over this side, electron on this side. This electron can shoot a photon to this end, so this electron knows that there's another electron on the side, and for example, it's attracting if it's two oppositely charged particles, and it's repulsing if it's equally charged particles. So the particle that is responsible for the strong force, it's what's called the gluon, and the name is it's kind of chosen well. It kind of glues things together because the strong force is so strong that it actually glues things together. And oh no, the pointer goes away. So let me do this again. I guess I have to do it this way. And then finally, the weak force is mediated by, which was already said in the video, by the W and the Z boson. And these are sort of heavy particles. And it's actually the fact that the particles are heavy, which is responsible for the fact that the weak force is weak, because heavy particles can't travel very far because they're heavy. And therefore, the weak force is really weak as soon as you go, any appreciable distance away between objects. Now, if you talk about these particles on the outside, The strong force is felt by all the quarks. So all quarks feel the strong force, but the leptons do not feel the strong force. Okay, so leptons at the moment do not interact by the strong force. Now, electromagnetism is felt by all the quarks and the 3 leptons. These are all particles that are charged under what you usually think of as a charge. But the neutrinos, they do not interact either via the strong force or the electromagnetic force. They only interact with a weak force, as do all other particles in the standard model. So every particle interacts via the weak force. Neutrinos only via the weak force, the leptons via weak force and electromagnetic force, and then the quarks according to all 3 forces.
We have a question in chat.
Yes. Oh,
the question is, are
gluons
gluons
smaller than, yes. Where do forces such a frictional norm? Yes. So let's start with the gluons. So gluons, no. So essentially all the particles that I have put here, at the moment, we consider them to be point particles. So what that really means, we have not observed them to have any size that we can measure. So they're smaller than anything we've measured so far. So in our theory, they don't actually have a size. So gluons have exact same size as photons. They just have a stronger coupling to their particles. So all the other forces, most of the, so for example, the frictional force is actually a force in the end. Comes in the end back down to electromagnetic force, because really what is happening when something has a friction, that there's some force, some chemical forces, if you want, that are exchanged between a thing that is on top of an object and below of an object. So that's one way you can have a frictional force. We call them van der Waals forces, and those are electromagnetic in origin. So the electrons inside the molecules, inside the atoms. Of course, there's also frictional forces literally by, things are rough, and sort of gravity could have an effect too, because I have to sort of move up and down. The question about how to measure something's size will come to that. I will talk about this in a second. So about the fundamentals, so these frictions and other forces, in the end, you can all boil them down. Most of them are sort of responsible. So essentially the strong force is because things are glued together, they essentially don't escape the nuclei. So they're really, you see the strong force only within the nuclei. And the weak force is so weak that we don't see it. So almost every effect that we see in everyday life is due to the electromagnetic force. Okay. Okay, so now you might ask, well, how do we know, that these are the particles of the standard model, that the standard model is the correct theory of nature? What do you even mean by it's the correct theory of nature? So how do we test this? And so let's actually go a little bit. You also saw some of this. So what I'm showing here on the left is an atom, and that is a size of about 10 to the minus 8 meters. Okay, so again, 0.088 zeros and then a 1 in meters. Sorry, in science, obviously we measure everything in meters and not inches and feet. And I'm European as well, so I don't really know much about inches and feet. And it's too complicated anyways. Anyway, so then if you look inside the atom, there is this nucleus. And the nucleus actually is a lot smaller. It's a factor of 10,000 smaller than the atom itself. But if you look inside of the nucleus, then you find that nucleus actually contains protons and neutrons. And so each proton and neutron is another factor of 10, roughly smaller than a nucleus. But then if you look even deeper inside, and as I said, we'll talk in a second about what I mean by looking deeper inside, you actually find that there's more particles inside, particles we call quarks, which are sort of bound together by these gluons into protons and neutrons. And then the strong force is also binding protons and neutrons together into nuclei. And as I said, we've not discerned, we've not been able, so we call this in science terms a substructure. So essentially a proton as a substructure consists of smaller particles. We have not observed any substructure of quarks whatsoever. Okay, so so far they are all consistent with being just point-like objects. No, decay in radioactive atoms is caused by the weak force. So actually, if you take a radioactive decay, what has actually happened, typically a proton turns into a neutron in a radioactive decay. And that is, and so if you now remember that a proton has 2 up quarks and a down quark, and a neutron has 2 down quarks and an up quark, that actually means you have a transition of an up quark to a down quark. That is sort of what is driving nuclear decay, and that is the weak force that is driving that. Okay, so decay in radioactive atoms, that is all weak force. Is there a limit to how small something can be? Yes, so there is the Heisenberg uncertainty relation, so to the size, how small something can be. So essentially what we mean by when we say point-like, we just say smaller than anything we've been able to test. That's really what we mean by that, and we don't assign a real size to it. Good. So if I want to do this, if I want to see 10 to the minus 13 meters and then see deeper inside, I need a pretty darn big microscope to see this. And we don't really need a normal microscope. So these optical microscopes are not going to do it. So what kind of microscope are we actually using? How do we look inside and check what things are made of? And this goes to this Heisenberg uncertainty principle, which I've just said, which essentially says that the uncertainty that I can never measure both the position of an object and its momentum with 100% precisely. And there is a relation that essentially says the uncertainty in my position times the uncertainty in my momentum is always greater than some value. It's called Planck's constant. And so if you take that and you think about it a little bit more, what essentially that means, if you want to probe small distances, you need a large momentum. And that is actually the same even in an optical microscope. If I look with an optical microscope, I look with, I can only resolve sort of sizes on the size of wavelength of optical light. So if I want to see something smaller, I need light with smaller frequencies. Okay, so you can think of this, the light as a wave, and if something is smaller than sort of the typical size of my wave, then there's no way I can see that with light. So, and essentially that means I need higher, so that you can, hard to explain, but at the end of the day, you need higher momentum. And so if you spin this idea a little bit further, that means if you collide particles at really, really high energies, you can actually see inside them with smaller and smaller, at smaller and smaller distance. Okay, so in the end, to do these microscope, we need to be able to collide particles at really, really, really high energies. And in order to get particles to such high energies, we need to accelerate them to those energies that come. We don't have naturally particles at those high energies. So what we really need to do is build an accelerator that accelerate particles and then collides them. Okay. So what do particle accelerators look like? Well, the first particle accelerator was built about 90 years ago. And here's a picture of that thing. So that is something here that's, now you can tell it was, well, I'm not going to say anything. It's about 20 centimeters, 25 centimeters long. So about this big in diameter, sort of from here to here. And I said, it's about 90 years old. Here, opportunity in the chat again. Where do you think the first one was built? First accelerator. Random guesses is fine. Austria, Germany, I see. Germany. Hey, not just because I'm from Germany does it mean it's, there's another thing that would get me excited. Where do you think it was built if I show you that picture? Berkeley. First particle accelerator was built in Berkeley by somebody named Ernest Lawrence, who was a professor at Berkeley and founded Lawrence Berkeley Lab, the lab that I now work in. And actually, how many of you have been to the Lawrence Hall of Science? If you actually look, nobody looks at that thing, but right when you walk in on the left, there is sort of this display. There's a chalkboard. I have no idea if you remember. I was probably much younger when you went, but there's a chalkboard. And there's actually a precursor of that accelerator. The first accelerator that Lawrence ever built is at the Lawrence Hall of Science. There's one in Lawrence Hall of Science, and I think the other one in the Smithsonian. Okay, so it tells you that there is some pretty cool stuff in the Lawrence Hall of Science. Yes, so the Lawrence invented the particle accelerator. And this is essentially all of particle physics until about the 50s happened all in Berkeley at Lawrence Berkeley Lab. After that, and we'll talk about this, you need bigger, if you want to go to higher and higher energies, you need bigger and bigger accelerators. And at some point, you couldn't just do this in Berkeley anymore on the Hill. And so then we went to other, then the next accelerator was at SLAC, down by Stanford. And the one after that was in Chicago by Fermilab. And now the biggest one is in Geneva, at the Large Hadron Collider, which we'll talk about. But I think it's pretty cool. So that is, that's Berkeley, and it's really famous in science circles for that. Here's actually what was kind of also cool. This is the original. I will talk about why they have to be so big now in a second. Actually, I don't, but remind me on the next slide. I'll answer the next slide. So here's actually after in 2003 or no, 2000, when was it? 2008 or something. This was always in a museum in London, this particle accelerator. And at some point, like about 10 years ago, it was sent back to Lawrence Berkeley Lab, and it's now actually at Lawrence Berkeley Lab. This is a seminar room right next to my office. And there, some of my colleagues were sort of marveling at sort of the first particle accelerator that really started the whole field of particle physics. So to probe the standard model, though, oh, and I should mention this particle accelerator, I said it accelerated protons to about 1 million electron volts. Let's not worry exactly what 1 million, what that really means. The important thing is what we need to do to test the standard model. We don't need 1 million electron volts. We need 1 trillion electron volts. So we need a lot more than that. And in order to do that, I need a particle accelerator that is about 5 miles large. Now, the reason why we need it to be so large is that so essentially what happens in these accelerators, let me actually show you on this side. So I'll come to the question in 1 second. And of course, if I want to do something 5 miles big, 5 miles is the size of towns, right? And so this is actually the Large Hadron Collider. And what you see here is a countryside in Geneva. It's actually half in Geneva, half in France. And you see here that this is sort of this new cyclotron, this new accelerator. And this is actually 100 meters underground. So this is just superimposed. You don't actually see any of this. This is just fields. But 100 meters underground is this particle accelerator. And so the reason you need this to be so big, because what are we doing here? So you can see these 2 rings here. And so what we're actually doing in these accelerators, we're taking protons going around in one direction and antiprotons circle around in the other direction. And then at some points in here, probably here where the green things are, is where they get accelerated. You literally take it because protons are charged particles. I put them in an electric field, and then I just give them a little kick with an electric field because they get attracted to the electric field, and then they get sped up a little bit. And then each time they go around, I speed them up a little bit more. And I need to speed them up to, I believe it is 99.999999 times the speed of light. So percent, sorry, 99.999999% of the speed of light is what I need to get these protons. So why do I need them to be big? Now can we come to the question? Because protons, as everything, wants to travel in a straight line, right? Nothing wants to go in circles. And in order to keep these protons in circles, I need to bend them with magnets. So essentially I use the magnetic force to change the directions of these protons. And essentially, and the faster something goes, the harder it is to change its direction. And essentially the largest magnets we have available can take a proton at the energies that we need them in and can only keep them on a radius that is about this big. So if I were to make it smaller, I just couldn't bend the particles anymore. They would just shoot out. Does that make sense? So it's really the strength of magnets that we have available. It's just magnet technology that we have that we can, which is essentially determining that size. So what I also now thought of doing, let me do one other video here. It doesn't have sound. I'll walk you through it. And then I actually want to show you sort of in Google Earth a little bit what the Large Hadron Collider looks like. So this is an animation that was made by some of us at Lawrence Berkeley Lab. And sort of it shows a little bit how we accelerate these things. So remember, going back here, you see sort of a ring here. See one ring here, and there's another ring here. And actually, if you were to look carefully, there's another smaller ring over here. So let's actually see how do we accelerate these particles. So what you see here is we inject. So we start with a particle over here, and it's protons. So we literally start with, okay, I will come to Raul's question about how did the first particle accelerator work then in a second. It's the exact same principle. You have a proton, the protons are tiny, right? And so they turn around and they were much lower energy. Remember, I told you we need 1 trillion electron volts now, and we only had 1 million before. So we were 1 million times less energy, which meant you can make them much smaller because it's very easy to keep these. These were very small, very, very slow protons for what we need now. And it was very easy to keep them in a circle, even with magnets at the time. Okay, so what essentially happens, we start essentially from a bottle of hydrogen, which is protons, and we shoot them, we just make them go into this direction. And then they enter this first ring here. And that, oops, sorry, I didn't want to do. And you can see here, this is a ring that is about 157 meters in circumference. And those the magnets, in this, with the current magnets that I have, I can get these things up to 1.4 GeV. A GeV is 1 million electrons. So I sort of just get them a little bit higher at what we could do back when Lawrence did it. Now, and it's just, the reason they're using this ring is because they have it available. They could make it much smaller than that. Okay, so we accelerate them up to these 1.4 million electron volts. And then once we have them here, we shoot them in the next bigger ring, which is sort of 630 meters in diameter, where we can accelerate them another factor of 25 more. So now we're 25 million electron volts. Once we have them here, we shoot them in the next ring, which is the accelerator that existed before the Large Hadron Collider. That was also an accelerator that they did experiments on, which is already pretty big, 6.9 kilometers in circumference. And I can accelerate them now to 450 GeV, 450 million electron volts. Sorry, all of those are, let me go back. GeV is 1 billion electron volts. So I started with 1 billion, so already 1 million times more than what Lawrence had, which is why I needed the 150 meters. And then at the end, I'm going to inject them into really the Large Hadron Collider, which is now this gigantic thing where I can really pull them up to 7 TeV, that is like 7 trillion electron volts. Okay, and then we let them circulate, we accelerate them, and we store them. And here is what it looks like, this tunnel. So this is the tunnel 100 meters underground. And I'll show you another picture of that in a little bit, where they essentially just travel through this tunnel. And you see here an animation of the proton with the 3 quarks inside. And then we sort of use magnets to take the 2 protons that come in opposite directions, and we aim them at each other and we let them collide. So we literally make them crash into each other at these ridiculously high energies. And then what happens when they crash into each other? Imagine you just throw stuff at each other, at some point just explodes, and lots of things happen. And essentially, because what happens here, because it's essentially Einstein's equation E equals mc squared. So if I have a lot of energy, so mass and energy are equivalent to one another. So if I have really high energy, I can produce particles with high mass. And so essentially by doing this, I can sort of collide these protons, and essentially the quarks inside interact with one another via the strong, the weak force, the electromagnetic force, any one of those forces. And then they can produce other particles. And then what we have in these particle detectors, there's the Atlas detector and a CMS detector, 2 detectors. And these are very finely instrumented. And I'm going to try to record everything about these particles that fly out. Where do they go? How much energy do they have? What type of particle is it? What is their mass? All sorts of things. As much information as I can, I record about them. And then I store it essentially on hard drives. And then we study those interactions. And we try to, from essentially looking at these fragments that came out, we try to then kind of put things back together and try to understand what were the forces that were involved in colliding this. It sounds really complicated, really is pretty complicated to do that. How do we diagrams? We will have, I don't know if you refer about Feynman diagrams. Are you talking about Feynman diagrams here? I will have some diagrams. Ask me again if I'm not answering the question, Anushka, okay? So this is essentially what we're doing here, okay? So we are, oh, I forgot, by the way, this is, for those of you who had trouble seeing this video, this is where I got this from. Okay, so the last thing I want to do is actually take you a little bit to the Large Hadron Collider and have a look at it. Okay, so let me briefly unshare my screen here and do another share and go over here. So I thought we start with something that is familiar to you guys and start at the Berkeley High School. But what I want to do is I want to take you on a trip to CERN. Okay, so let's fly from Berkeley. Let's fly from California. And I will put this also into the chat window and fly over. So what you see here, this is Europe, and this is Switzerland, and let's stay here for a second. So what you see, let me get my pointer, sorry, spotlight here. So this is Lake Geneva. This is the airport of Geneva. This is actually the CERN site where the buildings are, where the scientists sit. And these are various points of the Large Hadron Collider. And by looking at these points, you can probably imagine that the ring sort of does something like this. Okay. The border de France actually runs right through CERN. So the border de France is somewhere here. And I remember like a few years ago, I actually lived for a year. I was in sabbatical in CERN, and I lived somewhere right over here, right next to the mountains. It's actually really pretty. In the winter, there's like ski resorts over here. It's kind of really cool. So let me just show you two things. So first, let's actually go. It's kind of cool. So you can check this out yourself. If I get the chat, why is my chat now not coming up? Here it is. Sorry, there's two more questions. How do you extract the proton to accelerate? Yeah, so what we do, essentially what hydrogen is nothing but a collection of protons. And we essentially, there's sort of a way to focus these, essentially use, again, magnetic fields to sort of, you use sort of electric field, accelerate them a little bit in one direction, then use magnets to sort of make sure that they all kind of go in the same direction. And so that's really where we start from. You literally start from hydrogen, and you start let the protons go into a pipe, and then you slowly accelerate them and you focus them, what we call. And yes, it is also true, the answer here that we collide and these protons, but there's, as Anushka said in this thing, there's actually lots and lots and lots of protons that keep going around at the same time. And actually every one of these collisions, so they're put into what is called bunches with lots and lots of protons. And actually at these colliders nowadays, you actually often have like sort of 30, 40 protons all collide at the same time. And that is part of the complications, that you're trying to still extract only one of those collisions at a time. But yes, the answer was exactly right here. So let's have a look inside the LHC tunnel. So it's actually kind of cool. You can do street view inside of the LHC tunnel. So you can do this yourself, by the way. I'm just going to put this thing here in the chat as well. So this is the link to where I'm at right now. And so, you can just walk through this. Let me actually turn around here, walk a little bit in this direction. What you can see here, there's a line in Switzerland after all. So there's a bike lane, literally there's a bike lane. And when you actually want to access this thing, the technicians actually ride on bikes because it is, 27 kilometers is far. And there's not doors everywhere, right? So you can sort of see, this is the pipe where the protons run around in. And then every once in a while, you see sort of equipment, like for example, here, see quite a bit of equipment. There's, lots of different things here. There's probably cooling. There's vacuum, or the whole pipe is in a vacuum. There's probably vacuum chains here, vacuum chambers, and so on. So that's that. And then the other thing I wanted to take you, and so you can see this is literally underground here. This is where we just were. It was in the middle of fields. But what I wanted to show you is the Large Hadron Collider, because that is pretty impressive. So essentially what we're trying to do now, we collide these particles. And then, as I said, we need to see what comes out. And now these are these massively energetic particles. And I need to record everything that comes out. And there's an enormous amount of information that I'm trying to record. And so it's an incredible piece of equipment. You think of, you might have seen some sort of labs that you can see. This is much more impressive than your ordinary lab. So let's actually walk down here. So this, this is the Large Hadron Collider. I wanted the LHC. Let me actually, this is one. Yeah, sorry, let me find, here's Atlas. So this is Atlas. So let me orient yourself a little bit. So maybe let's set the scale for a second. So the scale, this is a door. Okay, so from here, and there's some steps. So here, this is ground floor. This is the first floor. Let's keep going up, actually. Let's look up. First floor, second floor, third floor, fourth floor, sixth floor, seventh floor, eighth floor. So this thing is 8 stories tall. Okay, so this is just an idea. It's really amazing. And if you walk a little bit closer here, you actually see that there's an enormous amount of electronics. There's cables like everywhere in this thing. Okay, so this is something that took about 15 years to build. There's about 4,000 or 5,000 people on this experiment, all working together to make this work. And so, you can do this on your own time. Go on Google Earth, type in CERN, and you get to where I'm just here. So let me, but I think it's pretty cool to see this. So I just wanted to show it to you. But let's continue with the talk. And let me get my spotlight back. And somehow my chat disappears every time I do this. Good, no more questions for them. Good, so let's continue. And so what I want to show you a little bit is how you can, just for you to get a feeling for what we actually do to test the standard model. So what I already told you, right? We already talked about this. We have strong interaction, we have electromagnetic interactions and weak interactions. In the weak interaction, there's 2 particles, the W boson and the Z boson, and essentially doesn't really matter. One is one is a charged particle and one is a neutral particle. Doesn't really matter at the moment what we're talking about. But essentially, it was a physicist called Richard Feynman, who was at Caltech, who came up with these Feynman diagrams. And these Feynman diagrams are a really beautiful pictorial way of sort of looking at the equations of the standard model. So for example, what this Feynman diagram tells you that there's a quark coming in, a quark going out, but the quark is emitting a gluon. So one quark is turning into a quark and a gluon. And then that means you can now put another quark over here, and that would really now explain how you transmit a force from one quark to another quark by exchanging a gluon. So these Feynman diagrams, they're pictures that you can really visualize what's happening. But essentially, every one of these objects, like every line, every vertex, is a mathematical equation that you can then also use to really do calculations. But what is nice about these Feynman diagrams is that you can sort of see in your imagine what will probably happen. So let's actually look at one process. So here is a process of how we actually discovered the Z boson. This was not at the Large Hadron Collider, much before, but we can look at it here. And so what you see here is I have 2 hadrons coming in. So for us at the Large Hadron Collider, these are 2 protons. A proton coming in here, a proton coming in here. And of course, in real life, they're coming in, they're flying on top of each other. But this is just sort of saying I just draw them in the same direction. And then what's really happening in the process is that it's not the 2 protons directly collide, but it's actually 2 quarks inside the proton collide. And then via this Feynman diagram, can actually emit a Z boson. So if you go back to my to this thing, you see that 2 quarks, a quark can emit a Z boson. And it's also 2 leptons can emit a Z boson. So that means I can have a Feynman diagram where 2 quarks collide, produce a Z boson, so they disappear. So it's a quark and an antiquark. They collide, they disappear, they make a Z boson, and then the Z boson decays again and makes 2 muons, a muon and an anti-muon. So muons are very special particles. They're like electrons, but heavier. And if you work out what that means in a typical detector that we have, it means that because they're so heavy, they don't interact with most of my detector. They essentially just fly through the whole detector. And I need a very special detector at the outer edges of that Large Hadron Collider that essentially has really dense material, so I can actually see those muons and make those muons interact. So these are called muon, muon detectors. Okay, and so what you should see if you see a muon, you see nothing in your detector, but then all of a sudden there's something that on the outer detector that you probably see something in. And so let's see how something like this actually looks like in the detector. Let me first answer the question that we have here. We have different types of detectors for each particle. It's not for each, there's different parts of detectors that detect different things. So there's one detector that sort of tries to measure electromagnetic energy. So energy that is lost in electromagnetic radiation. So by essentially emitting photons. There's another, so that can sort of, so that is essentially detecting the energy of particles that that essentially don't have a strong force interacting with them. There's also a what is called a calorimeter, an energy detector that measures the energy that is lost by the strong interaction. So by sort of protons and neutrons going through my material. And then there's detectors, special detectors that try to measure the location where particles go through. So they can sort of leave tracks. So the first one measures sort of where particles are and where they move. These detectors I just talked about before, they measure the energy of these particles. And then there's these muon detectors. And essentially by combining that information, if I know the momentum of a particle and know the energy, I can also construct its mass. Okay, so it is sort of, it's not that I have a different detector for each type of particle, but I have different detectors for different types of measurement. And then if I combine them all, I can get a lot of information about the type of particle we see. Absolutely. Conservation of charge, we constantly produce antimatter at the Large Hadron Collider. Here, muon, antimuons happens all the time. So let's look at this detector. So here what you see, this is actually not quite this. This is an event, what I'm showing you here, where I think there were two more, let me see what this is. Yes, there were two more gluons radiated, I think, of these two quarks. And so what you see here is look at these two red lines. So what you see, I've drawn these red lines, you don't see any detector. So remove the red lines in your mind. But what you see here is that these three parts of the detector are lighting up. So that says that something went through this detector. The only things that go through this part of the detector are muons, because all the other particles are stopped inside of this part of the detector. So what you learn from this experiment, from this measurement, there was a muon here, and there was another muon here. And then you also see that you had here, this green thing is this thing that measures electromagnetic energy. The red thing is the thing that measures hadronic energy. So you see there were also two particles, two things that deposited had both electromagnetic energy and strong energy. These are two jets, two strongly interacting particles that happen. But this is essentially a Z boson that you see here. And then through careful measurements, I can determine the properties of these particles, the mass, the couplings up to other particles, the properties. Now, how do I actually do this? And I can't just look at one of those events and know and learn much about this particle. But what I can do is I can look at many, many, many events and look at the distribution of what I see. So let me say a little bit more of what I mean by here. So imagine I look at many of those events and I plot, essentially, I take the momentum of these two particles and I call what is called an invariant mass. I literally add the two momenta together and I square that. Okay, so this is something that is called an invariant mass. And what we can work out essentially, because these two muons come from a Z boson, so essentially that means the two muons, the mass, the invariant mass of those two muons has to agree with the mass of that Z boson that they came from. So by measuring the invariant mass of these two muons, I can measure the invariant mass of the Z boson. Okay, and so what you find if you now plot, you take each one of those events and you plot its mass, and then you plot a histogram. So you say, how many events did I see that had invariant mass of 80 GeV? And how many did I have that had 81 GeV? How many did I have 82 GeV? So what you see here is the invariant mass on the right and how many events I saw for a given invariant mass. And what you can see here is this shape. This is called a Bright-Wigner shape. And this is precisely what we would predict of the distribution that would come from a Z boson. The center, what we'd expect is that this distribution is centered at the mass of that Z boson. Okay, and so from this is precisely where we can measure that the mass of the Z boson is about 91 GeV. And from this width, that is giving me an idea of essentially how much these Z bosons can decay. So essentially this width gives me information about the coupling of the Z boson to other particles. Okay, so by studying distributions like this, I can extract properties of these particles. And that's essentially what we do at the Large Hadron Collider. Okay, so camera's histogram, can you be a little bit more, what do you mean by camera's histogram? Am I missing something? Why don't you, whoever asked the question, maybe just put something, is this a technical term, Cameron? Oh, is there, okay. No. So essentially, you see all these particles. So let me ask that question first, because I know how to answer the question. Is essentially all these particles live. Remember, in the video at the beginning was said the only particles that we actually see is protons, neutrons, and electrons. These are the only particles that are actually stable on sort of galactic timescales. All these other particles decay way too fast. So essentially, by the time they kind of hit my detector, they've already decayed. They live so short that I never see them in real life. So there is really only sort of see these decay products of particles. Okay, now this was really what we call a very clean measurement. I see this and I directly measure. Yes, so then it is, yeah, so I think a histogram, the way I use it is really sort of in the, yeah, it's the same thing as a distribution of light in an image. It's really, I literally just count, like how many times do I see a certain occurrence? You can do a histogram, you do a coin flip, you can record how many times do I see heads versus tail. That would be a two-dimensional histogram with 2 bars or something. You can think of it as a bar chart. But in many times, there's actual other processes. So here, essentially, what I told you, if I see 2 muons, then almost all the times they come from a Z boson. This is why this is such a clean measurement. Most of the times, actually, though, when I do a measurement, there's many other processes that can give me the same events that I see. And I need to now make sure, well, is it really the particle that I'm looking for that I'm seeing, or is it just something else? So here is, for example, again, I'm measuring, don't worry what I'm measuring some quantity on the x-axis. And again, I'm counting the number of events. Okay, so, 1,000 events here, about 100 events here, and so on. And what this particular analysis is trying to find is this red signal. So a signal that looks like this. So I make a prediction as a theorist. What is the signal that I'm trying to find? But the problem is, let's say I'm trying to find the signal over here, that there is, so this gives me, so this is a logarithmic plot. This is maybe 20 events. I expect 20 events, but there's 1,000 events from some other process like this Z boson plus jets. And so I have absolutely no hope of seeing this, right? Because all I would see is a teeny tiny, 20 events more of these 1,000 events. And that is very unlikely to be statistically significant. So what I need to make sure, however, when you go out here, that's what we call a tail of a histogram. There you now actually see that these red, that the number of it, that the red process, doesn't really matter what it is, has an appreciable amount of contribution. So whether this data point sits here or down here is actually significantly different. And then I can actually detect whether that red contribution is there or not there. And I can measure the strength of that red contribution. However, you do have to be very careful. Imagine I get the prediction of that blue signal wrong, and the blue signal is just maybe off by a factor of 2 out here. Then all of a sudden, I think I'm seeing the red signal, but really all I'm seeing that I actually just predicted my blue background wrong. Okay, so to make sure we're really seeing the red signal, we need to make sure that we understand the background, which is here mostly the blue distribution really well. And this is actually much of my work is in sort of developing tools to make these precise calculations. So essentially, making a precise measurement only helps you. We can also make a precise prediction for what you expect to see. Otherwise, it doesn't really help you very much. Are there quantum effects you have to take into account when you're analyzing data? Yes. So essentially, all of these calculations are all quantum calculations. There's large amounts of quantum interference effects that are happening here. But then the actual observations that I'm making, those are classical things. So I'm literally seeing, I don't know, at the end of the day, all of these signals are sort of voltages in some device or something. So at the end of the day, what we're recording is, so essentially these quantum effects are happening at really short distance scales where I need to make my calculations, but it's not that the detector itself, it does not have to be a quantum detector per se. What do the other particles decay to? They all in the end decay into these 3 particles that we know: protons, neutrons, well, photons as well. So protons, neutrons, photons, and electrons, essentially. That's what they all decay into. And that's in the end, everything that I'm seeing is just these particles. And I'm inferring everything else from what the distribution of these particles look like. Okay, so I've explained most of these things that I have in here, how we sort of try to measure the forces, the masses, and so on. But I want to talk a little bit of the Higgs. And I am realizing I am about 1 hour in now. It's a lot of questions. If you guys are okay, I can try to wrap up quicker. I'm happy also to talk longer. That's up to you guys, what I should do. So talk longer? Okay, I'll just keep going. Don't feel bad if you have to leave. I won't be offended at all. But let me keep going. Let me talk a little bit about the Higgs boson. And the Higgs boson is special. And the Higgs boson is what we understand is the particle that actually gives mass to all these elementary particles. So I just said that there is these particles at mass, and it's really that Higgs boson that gives the mass. So for the longest time, we had a standard model theory, and we knew that there was a part of the standard model that was responsible for giving mass to particles, but we'd never, and we sort of predicted that there was a Higgs boson, but we'd never observed that particle. And here is the person, here's a quote from Peter Higgs, who the particle is named after. And I think he explains it very well, what is so special about the Higgs particle. The Higgs is not a force particle, but as I just said, it gives particles their mass. So let's just read that quote, and then I'll go into it a little bit more. So the way that the background fields, which is these Higgs particles, generates mass is rather like the way in which when light passes through a transparent medium like glass or water, it gets slowed down. It no longer travels with the fundamental velocity of light c. And that's the way to think of the generation of mass. So let's try to understand a little bit what Peter Higgs here is saying. So the first statement, he's saying that the Higgs particle is a background particle. So that really means that is everywhere in space. So all of space is permeated by this background particle called the Higgs particle. And one important property of this Higgs particle is that it has different couplings to different particles. So for example, an up quark has a very light coupling to that Higgs particle, whereas a top quark has a much, much stronger coupling to that Higgs particle. And we don't actually understand where these numbers come from, but we can measure the couplings. And then what happens, what the Higgs particle does is the stronger it couples to a particle, the more it slows down that particle. So you can sort of view this as sort of, imagine you shoot a bullet into water, and then that bullet will just kind of get slowed down. And if you make it a more viscous fluid, so it couples more, then it kind of gets slowed down more. That's sort of how you should view the Higgs particle. And essentially, you can then understand in the end through Einstein's theory of relativity that slowing down a particle is kind of the same as giving mass to that particle. Okay, so that's really what a Higgs particle is doing. So it is sort of something that's everywhere in space, and particles have to travel through it like a molasses, and then it gives mass to these particles. And yes, all of space, well, I wouldn't say it's made up of Higgs particles, but it contains Higgs particles. That's how I would word that. And so, as I said, we had for the longest time a theory of the Higgs particle. Peter Higgs did this back in, I forget now, in the 70s or even before that. How is the Higgs particle different than the Higgs field? It's the same thing. So this is essentially in quantum mechanics that essentially this is what we call particle wave duality, which you probably have heard of. Essentially, every particle is also at the same time a field. You know, so you can think of light as being electromagnetic waves, so it's like a field. Electromagnetic field, but you can also think of it as photons, which is particles. And there's a duality. Essentially, those two things are the same thing. And that is really what quantum mechanics does. Is it possible that something can avoid interacting with the Higgs and have zero mass? Yes, the neutrino. The neutrino is a particle that does not interact with the Higgs at all. And therefore, the neutrino is very special. It actually has no mass. Or it actually has a tiny mass, but it's not that its tiny mass is not explained by the standard model, or not by this interaction. It's not explained through the Higgs. So there's something else that is giving the neutrino its tiny mass. Other kinds of antimatter have zero mass. Only antineutrinos have also zero mass. All other antiparticles have the same mass as the particle in the antimatter too. Okay, so I just want to show you this Higgs particle. So essentially, so this is now the same thing. I'm trying to take a Higgs particle. I had I lost this slide. So I can essentially draw a Feynman diagram again, where you can draw a Feynman diagram where the Higgs particle can decay into 2 photons. And by the same thing as where I showed you, Z boson can go to 2 muons. If you measure the invariant mass of these 2 photons, you should expect a peak with a center of that peak centered around the Higgs mass. Now the problem is, it's very easy to produce 2 photons at the Large Hadron Collider, and it's very rare that a Higgs boson produces 2 photons. It's very rare that we produce a Higgs boson in the first place. So what you expect is actually lots of photons. The distribution and plotting the invariant mass of these photons, you expect lots of photons from all sorts of processes. This is what you see here. And then you expect there's a teeny tiny blip of a little peak that comes from the Higgs boson. And in order to see this, I need to make that blip big enough to actually see it over sort of that background, okay? And so this is the discovery of the Higgs particle back in 2012, almost 10 years ago. And what you see here is in red curve is the prediction of the background. And then here is what a Higgs particle with a mass of about 125 GeV would give you as a blip. And so you can see how hard it is to see this, right? If I wouldn't show you the red lines, you might not even see this. Just, is there a peak here? Maybe there's a peak over here too. Is there another peak over here? Right? And so you have to do a very careful statistical analysis to really convince yourself that this is actually the case. But when they announced this, this was what we call statistically significant. So the probability of this being coming from a random fluctuation, like all these other things, statistical fluctuation, was less than 1 part in 10 to the minus 5. And that's what we call then a discovery of the particle. So it's very, very likely that comes from the Higgs particle. And if you do the same plot now with a LHC, this will look like this. Okay, there's a gigantic peak sticking out here. So there's no question that the Higgs particle is there and it has the strength that we want. This is just the seminar when this plot was first shown. This is at CERN, the auditorium at CERN, and the guy here in the back, that's Peter Higgs, who was invited to this. And I think these people started to line up to see this talk, I think at 8 p.m. the night before, and they just slept in sleeping bags in front of the auditorium to be part of this historic event. And then, of course, as many of you know, the next year, Peter Higgs won the Nobel Prize with other people who also predicted the Higgs particle. So it was a pretty big deal back then. Very good. So last thing I want to do, if it's okay to go on another 5 minutes or so, is, I just told you everything that works so well about the standard model. So does it describe everything? Does this little beautiful picture describe everything we know about in the standard model? And the answer is a huge resounding no. And I'm going to give you one example. There's actually several things that you can't describe. I already mentioned neutrino masses, which we know of mass, we can't explain. There's something about a question is, why is there just matter in the universe and no antimatter? And the normal thing, we never see antiprotons anywhere, right? We just see protons. We never see sort of, I don't know, a car collide with an anti-car and go off and explode, right? It never happens. Something for another talk. I want to talk about dark matter, which I'm sure all of you have at least heard the word dark matter. So what is it? And how do we know it exists? So to do this, I just want to show you something that probably some of you have learned in school or will learn maybe at some point. It's like Kepler's laws. It's essentially how do planets move around the sun. So essentially it's a calculation you can do. It's conservation of force. You essentially say, well, there is a gravitational pull. The sun pulls on the Earth. But then because it travels around, there's a centrifugal force that wants this thing to fly off. And I get a stable situation if the centrifugal force is equal to the gravitational force. And you can then say at what velocity is that happening. So the centrifugal force is mv squared over r, depends on the mass of Earth, let's say. The gravitational force depends on the mass of the sun, m, the mass of Earth, and it falls up like 1 over r squared and depends on the gravitational constant. Now you solve this equation, so you see the mass of the Earth is canceling out. So it's the same for Earth and for Jupiter and for Saturn, for all planets, it's the same. And if you work it out, you find that v squared is equal to gm over r. You can do this a little bit more, and now imagine I didn't have a sun, but I had some distribution of mass inside of here. So imagine there was some gigantic dust cloud or something that's pulling things in. Then actually the formula is exactly the same, but instead of having the mass that sits here at the center, it's the mass of all the stuff inside the radius of where that planet is. Okay, so this is a formula that just comes from, grab it from Newton's laws, essentially that v squared is g m of r over r. So if I can measure the velocity of an object, then I should be able to predict its mass that is within the radius. Or the other way around, if I can measure the mass, I should predict the velocity. So I can check for consistency. Is that equation actually observed or obeyed in the universe? And so let's look at a sort of a scaled up solar system. That's a galaxy. Okay, so I have lots of stars and they sort of orbit around one another, these spiral galaxies. But it's the same thing. There's mass, and essentially these stars out here are gravitationally pulled towards the center, and then that's why they orbit around. And I should be able to relate the velocity of stars over here to the mass. And I can see the mass, essentially, I look at the stars, I look how many stars I see, and I can estimate, we know, given how bright stars are, how much they weigh, so I can calculate how much mass there is in this galaxy, and then I should be able to check, is the velocity of these stars equivalent to what I'm seeing here? And so this is something a woman called Vera Rubin did, and she had incredibly precise measuring. It's just a marvel. You think about it, you're measuring the velocity of stars in a galaxy, right? It's pretty remarkable that you can do this with error bars that are this small. But anyway, she did these measurements here that measure the velocity of stars and then compared it and then she plotted them as a function of where they are in the galaxy. And just by using Kepler's laws, you would predict the velocity to follow this dashed line. And what Vera Rubin found, that's just not at all what the prediction is. It just looks like this. And now there's other measurements that are happening here. So somehow stars move way faster than we predict them by the laws. And this is not due to gravity being wrong. This is just something isn't right. And now if you go back to the formula, if stars move a lot faster, depending on their velocity, and gravity is right, that means that the mass has to be a lot bigger. So remember that mass that came here was calculated from what I see, from the stars that I see. So somehow there's a lot more mass than what I can see. And that is what dark matter is. It's essentially mass. It's gravitational things that interact gravitationally, but they don't interact via the electromagnetic force. Okay, that's what dark matter is. I will come back to the question at the end. Let me finish the talk so I don't go too long. We can go through the talks for the people interested at the end. Okay, and now you can calculate from this, well, how much dark matter is there? Is it a lot? It kind of looks like a lot, right? It's a lot bigger than what I see here. Well, it looks like a factor of 2. If we actually do it and look at all observations that we have, it turns out that of all matter in the universe, only 15% is the normal matter that we see, like stars, planets, and so on. 85% is that stuff that we don't see, that does not interact electromagnetically. Now, what is interesting, there's no particle in the standard model that can explain this 85%. So, it's kind of very humbling. I just told you we've made this enormous progress. We understand the standard model, we understand everything. And now I'm telling you, we really only understand 50% of the universe. And actually, there's a whole nother thing that I'm not going to talk about. There's also a component that we call dark energy. That is also something we know nothing about. And really, normal matter is only a few percent of the total energy in the universe. So that is the part that's incredibly humbling. And so very, very briefly about dark matter, let me go over this now a little bit quicker, so I just told you what we know is dark matter interacts gravitationally, but not by the electromagnetic force. So there is a possibility it's a particle that only interacts by the weak interaction. The answer here, by the way, Daniel, is we know how much is there essentially from things like this measurement. We could do that measurement. We know how much things pull on the star gravitationally. So we know because gravity is proportional to mass. So we can measure how things are pulled gravitationally. That's where we get that measurement from. Okay, so if you remember, I did tell you there's 3 particles that actually don't interact via the electromagnetic interaction or the strong interaction. However, I also told you that these are massless particles, so therefore they also really don't interact by the gravitational interaction. So neutrinos are not dark matter. They're way too light to be dark matter. So that means there is no particle in here that can describe dark matter. Okay, so it could be, of course, some new particle that's like a neutrino. It's just a lot heavier. And that is what we call a weakly interacting massive particle. It's a WIMP, but that's just really, we don't know. And so we've been actually searching for dark matter particles for a very, very long time. And how do we search for such a particle? So we know, or we kind of can hope that if there is some weak interaction, that maybe we can have a process that looks like what I showed you for the Large Hadron Collider. Maybe two dark matter particles can collide and then produce two standard model particles. And then I can actually do various ways of searching for this. So assuming this interaction exists, I can now search for it. So for example, I can go, oops, that is the wrong way. Oh, what's happened here? Oh boy, I didn't switch it. This should be standard model over here and dark matter over here. I'm sorry. So collider says I collide two standard model particles, the protons, and maybe I just produce two dark matter particles every once in a while. And for example, it could be a process like this. Two quarks collide, radiate off another gluon, and then produce two dark matter particles. And dark matter particles don't interact electromagnetically, so I won't see them in my detector. So what I should see is sort of a particle that flies out in one direction and by conservation of momentum, but I see nothing on the other side. And so by the conservation of momentum, it tells me there was something on the other side that didn't interact with my detector, and that could be dark matter. Now, this is a real event from the Large Hadron Collider, but that's not dark matter. That's actually just a muon and a neutrino that we're seeing here, because the neutrinos also will have the property that just escaped the detector. So, but there's lots of searches at Atlas and CMS to find these dark matter particles. None of them have found dark matter particles yet. Okay. There's another way to do it, and again, it's just wrong. It's indirect detection, so the arrow should now be the other way. I can also imagine that maybe two dark matter particles can collide and produce two standard model particles. And then, you know, there's a lot of dark matter out in the universe. So every once in a while in the universe, two dark matter particles should collide and then produce standard model particles. And maybe these standard model particles now fly towards Earth and I can see them. And that is something that we also do. And for example, one experiment that does this is called the AMS. It's a spectrometer that looks essentially for some of these particles, and it's actually mounted on the International Space Station. The reason I go into space, because I want to get rid of what is called cosmic rays, and I want to get rid of things that have like contamination from the atmosphere. Okay, so that's the indirect detection. And then the final detection is I might also look for dark matter particle colliding with a standard model particle and producing another dark matter particle and standard model particle, but maybe I observe that this standard model particle starts to move in a different direction. So it's some process like this. I have a particle come in, it collides with a standard model, say proton inside of some water or something, and I measure this outgoing particle and something happens. And these are actually experiments that are being built. Let me go over so I can finish up and do this. These experiments have to be built. These are very rare interactions. So for example, if I try to see how often might this happen, so if we had really something that interacts with a weak interaction, I would expect it of a ton, like 1 ton of material. I would probably see 4 events one event every 4 days. And the problem is there's cosmic rays coming in like all the time. So in order to get rid of backgrounds, I have to sort of reject a lot of backgrounds. And so these experiments typically go deep underground where all the cosmic rays are blocked. So this is actually something in South Dakota. There's a very deep underground mine, a mile deep. And this is actually where typically those experiments go. So we observe things down here because these dark matter particles, they don't interact with anything. They just go right through the Earth. Okay, and so people have looked for dark matter particles in those interactions. And again, we haven't found it. So despite great experimental efforts, we've not found dark matter particles yet. That leaves many possibilities. It could just be too heavy or too light to be sensitive to the current experiments that we have. It might just interact much weaker than what we can probe, right? If it doesn't interact at all, we can only probe it gravitationally. It might not be a single dark matter particle, like what I just showed you sort of assumes there's just one dark matter particle. Well, maybe there's a whole nother dark theory that has like dark gluons and dark photons and dark quarks and dark leptons and everything. Could be a whole dark standard model. We don't know anything about what's happening here. All we know is that there's more mass in the universe than what the standard model describes. It might also just feel gravity and nothing else, right? Then it will be kind of hard to find, even though there's some ideas even to look for that. So this is really one of the great mysteries of science, is what is dark matter particle? And that is, you know, one of the many things that sort of the particle physics nowadays is addressing. So let me end here, and I'm happy to stay as long as you guys want, and I can try to go through some of these questions that you guys have. So very good. But I do want to give everybody a chance to also sign off if you want to sign off. But as I said, don't feel bad for me. I'm happy to stay on.
Can I ask a few questions?
Absolutely.
So if detecting things with a weak or heavy frequency in an array of an area that's always getting bombed by different types of rays from exploding suns, planets, or different type of UV energy, then how exactly do we think of catching one particular type of particle wave in a bombardment of particle waves like a Tokyo expressway?
That's a really, really, really good question. So let me go into, so one thing you're seeing here, okay, so we're essentially putting, so let's take this dark matter particle, this dark matter experiment as an example. So one of the things that bombarded is cosmic rays. Okay, so I go very deep underground to have this. This also blocks out lots of other things that we do on Earth, right? That could produce particles. There's still an enormous amount of backgrounds. First, there is still cosmic rays that actually go down here, and I need to block them out. There's also lots of other things that can happen. For example, I can have actually radioactive decay, or I can have some impurities in my material that actually something can happen. There could be small radioactivity somewhere in my lab that is actually producing some of these particles can give these kicks. So there is an incredible amount of work done to suppress all of these backgrounds. So for example, if you look at this experiment, I'm actually putting this experiment, so this is what is called the active detection volume. This is where I look for things. And now this entire experiment is put in a humongous tank of water. And water is essentially, again, a pretty good shield against other things. And so essentially, I'm embedding this in water to sort of block out, again, any other things. And then also I can sort of see if, something comes in here and it sort of already interacts, leaves a trail of interactions in the water that this whole thing is sitting in, then I know it wasn't a dark matter particle, most likely, but it's something else. But yes, this is the whole name of the game of these experiments, is more exactly about what you just worried about. It's suppressing all of these backgrounds. Now for the Large Hadron Collider, exactly the same thing, right? So if you think of my gigantic detector, right? So let's just look at that picture here, like one of these event displays. For example, there's cosmic rays going through that thing all the time. But a cosmic ray will look like a straight line that comes from somewhere up here and just go down. And so I can actually veto those. I can just see that this is, for first, most of these cosmic rays will never hit right through the center. So, I have a gazillion of events that just do this. Those are cosmic rays that are just vetoed and are not included. So, but it's an enormous amount of work to worry exactly about this. Any other questions? Let me see. So I can also, feel free to interrupt me. I'm just reading some of the questions. Yeah, so photons are massless because they don't interact with the Higgs particle. Absolutely. So now, if you're really careful at what I just talked about, remember I told you actually the Higgs, what we first observed the Higgs in is in 2 photons. So you might say, hold on. A photon is massless. How can a Higgs couple with a photon? The photon is massless. Well, actually, if you're really careful, what is actually happening in this process is a Higgs particle that goes to 2 top quarks, and these 2 top quarks form a loop of top quarks, and then the top quark radiates 2 photons away. So that's really how the Higgs particle couples to those photons. So there's no direct coupling of the Higgs particle to a photon, which is why it doesn't get any mass. Let me see, what else do I have? I don't know, it says, doesn't Mon describe this phenomenon? I'm not quite sure what phenomenon here we're talking about. Yeah, so the question, how much, but we know how it's there, so that was gravity. How do we know if it were dark matter or neutrino? So essentially we can compute, we know how much matter there is, and essentially if it were a neutrino, it is way too light. A neutrino could never give you enough dark matter than what we observe in the universe. So the neutrino is really a tiny contribution to dark matter, if you want, but it's way too small. What do we have? Why not a frequency, Daniel? I don't understand that question. Maybe that's you can ask it again.
It was really just much of my own theory, but consisting to the only thing that we know about it is very vague. It was just my own theory, but what if we're seeing it the wrong way?
Yeah, so essentially the main thing, so the way always about the science is the difficult questions are if you're trying to understand a phenomenon, you always have to make sure that whatever explanation you come up with to describe a new phenomenon is in agreement with everything else that we've seen in the past, right? Because everything, or it has to be consistent with every experiment that we've done. And so the main thing here is like typically if it's just, typically just the frequency could come from a massless particle like a photon, and that could not be dark matter because it doesn't have mass. So you have to explain the gravitational interactions that thing is. I'm now not saying that there's not another explanation, right, than what we have. I'm not saying that, but you have to, and there are there's many other explanations of dark matter, which is not this wind thing, single particle that I had here. But you always have to sort of make sure that you're sort of checking consistency with all previous experiments. Long question here. Let me try to read this. Was there another point part measure size above an infinite number? Yes, that is absolutely possible. That this is the case. In fact, we do believe, right, that given that there is, so the question is essentially, is it possible that every time we go to the next energy, we see again something new? Absolutely, that is possible. At the moment, we know that the Standard Model is correct at the energies that we can measure, except for dark matter. But we actually had, when we built the Large Hadron Collider, we actually expected that once we go to the energies that the LHC can probe, that we find all sorts of other new things. And the reason for that is that if you look at dark matter and if you sort of predict if it is a weakly interacting particle, what would the mass of a dark matter particle be? It would be about the mass of its mass would be of the same size as the energy we can probe at things at the Large Hadron Collider. And there's actually another mystery in particle physics that I didn't talk about, which is why is the Higgs boson so light? It's called the hierarchy problem. It's a complicated argument, but essentially because the Higgs is a boson. It's the only boson that it has. So it's a spin zero particle. There's no other spin zero particle in the Standard Model. And there is no explanation that we have for why a spin zero particle should be light in principle. So that means if you actually do quantum effects on a spin zero particle, you would expect it to get an arbitrarily large mass. So it's actually a pretty big mystery why the Higgs particle is as light as it is. And there was a theory called supersymmetry, actually also invented by somebody in Berkeley, Bruno Zumino. And that sort of predicted that there is a whole nother set of particles. So essentially, once we go to energies of order of the Large Hadron Collider, many people thought that we might see a whole nother Standard Model come into existence. So essentially, every particle has a supersymmetric partner to it. And so the whole particle spectrum, all the particles get doubled out or even more. And then what is beautiful about that theory had a very natural dark matter candidate. There was a natural particle in that supersymmetric theory of a stable particle that was not electromagnetically interacting. But, great theory, but it was just, so far we have not observed it. We have not seen any evidence for supersymmetry at all in any experiment done so far. So, and physics is the science of nature, and it's not a science of who comes up with the most beautiful theory. So essentially, if data doesn't agree with a theory, then that theory is just wrong. And so now I'm not saying that supersymmetry is wrong, but it's just not right at these scales at what we have. And it's probably unlikely that supersymmetry is explaining the dark matter particle.
Well, dark matter itself is something I can't see. So how exactly I'm going to find something or even try to calculate the mean possible integer of mean? Wait a moment.
Are you talking to me, Daniel?
Oh, sorry. I didn't know I was still unmuted.
Okay.
So what still confuses me about the whole study of dark energy, dark matter, or anything that's not seeable or easily recognized is that we're usually referring to it as a particle, something that is still there, even though we can't steel-proofly sense it. And if that's the case in general, then if we can't still sense it, how do we even know we're actually looking at what we're supposed to? That's kind of been my theory for a long time since I began.
So it's an very interesting question. So let me throw a question back at you. How do you know that gravity is that Newton's laws are right, or that Einstein's theory of relativity is right? Right. So the only way when we call a theory right, what we really mean, it's not wrong. But we can never actually prove scientifically that something is right, because right means it will never fail any experiment, sort of by construction, and we clearly cannot predict the future. There's no way I can prove to you that any experiment you can ever do will not violate something. So I think when we call something right, so typically when we call something a theory, is when we've come up with something and then we made a lot of predictions. So it's not good enough to say, oh, I have many experiments and now I come up with a theory that explains everything I've seen in the past. Typically, you have to predict something in the future as well. You have to say, well, if you do something else and you run this experiment, I'm going to predict that you will see this. And in particular, in the standard model, at some point in the 70s, somebody won the Nobel Prize for the standard model. It was Weinberg and Glashow. So why did they win the Nobel Prize for the standard model? How did people decide the standard model is right? What they predicted is the mass of the W and the Z bars. They said if our theory is right, then there's a very particular mass that these particles have to have. And they made lots of other predictions. Then people went and they built one of these colliders to look for these particles and measure their mass. And the prediction was just spot on. Okay, so this is sort of typically what you have to do. Remember, in Einstein's theory of relativity, it was also at some point he predicted some deflection of light that then was observed in some solar eclipse later. Okay, so you sort of have to make a prediction for the future. So typically, explain a problem that exists. But you're right, you can't really say that a theory is right, and there's always alternate explanations for any theory.
Well, if that's the case, well, then I'm actually going to put in my own little prediction.
Mm-hmm.
Once we finally are able to find a definitive proof that it's actually out there and actually something that we can recognize, it won't be in the same way that we originally thought it would be. More of a more complicated way, more than simply putting it as a detectable photon, but more as a more sophisticated, different type of wave. Nature has always confused us in many different type of waves, so I'm guessing, and I'm putting down just my own prediction that it won't be everything same as normal laws of physics.
Absolutely. So let me answer Anusha's question: how to use quantum computing to further this research. Interesting question. It's so essentially in these, remember I told you at some point is I'm doing these calculations here, okay? And what I said is we need to make a prediction of this, say this blue background, because if this blue background was a little bit larger, then so what I'm saying is if I measure, so imagine the red signal weren't there, and I measure the data to be above sort of this yellow thing, well, it could also just be that I just made a wrong prediction for this background and the data is actually green without this. So what that means, we need to make precise predictions of these backgrounds. And there's actually for several of these predictions, our calculational techniques are essentially not powerful enough to make these calculations. In other words, there's quantum effects in some of these calculations that we're essentially not able to include using sort of classical computers. It's just literally our computational power isn't strong enough to make these precise predictions. And we're now getting sort of to the point where sort of these small effects actually become, of the size of sort of experimental uncertainties. And what I'm sort of looking at in the quantum computing side is it possible that quantum computers, which is of course a whole nother talk, I'm even happy to give to you guys at some point in the future if you're interested, can include these quantum effects. So that's essentially what I'm investigating. Could a quantum computer, does a quantum computer have the ability to include effects that a classical computer could not? Now, of course, quantum computers are way far in the future, right? This is not something, we're not going to have a quantum computer in the future. I mean, I should take that back. We do have quantum computers now. IBM has built lots of quantum computers, but we don't have quantum computers that are powerful enough to really, supersede classical computers yet. We probably won't have for a long time. But, it's an interesting question. We need to think now for, what can we use 50 years later? Because, things do take a very long time to develop the technology for. So this is sort of where I'm going with quantum computing. So it's still sort of trying to understand particle physics, but sort of using new tools. And it's kind of cool to think sort of about quantum mechanics, and quantum computers are really fun and kind of weird in many ways. Great. Any other questions you guys have?
So this is kind of
Yes.
unrelated a little bit, but like Anushka and I are reading a book called The Black Hole War, and one of the things it explains is about world lines, and we were wondering what the world line of a black hole would look like.
So really what a world line is, so I'm not 100% sure now what the book is talking about, but essentially what a world line is essentially a, how should I describe this? It's a trajectory in time and space. So imagine you can say, if I throw something, right, it changes its position, but at the same, so it's essentially I'm trying to trace the position as a function of time. I'm trying to draw that line. That is what a world line is. And so, I'm not sure if that is what the book is referring to, but that is what I would think. Now, black holes are fascinating objects. So essentially, what black holes are, and this now really gets into sort of where quantum mechanics and it's a gravitational effect. So first of all, black holes have all to do with the part that I didn't talk about. It's all gravity. And essentially what you can show is that light is bent just gravitationally, because essentially what gravity really is, it sort of changes space-time, right? So even though a photon doesn't have any mass, but because I'm actually changing space-time, okay, my screen went black. Maybe I actually stop the share right now, and then we can just talk a bit. I see you guys better. And so essentially what you can show that if gravity becomes too strong, then a light cannot escape anymore from a black hole. Essentially it becomes so strong that it spends so much it can never escape. And that's really what a black hole is. So it's a pure gravitational effect. Now there is quantum effects in black holes, and there's actually a whole set of research, and I think somebody put the word string theory somewhere, and I can't remember now where it was. And essentially what string theory is trying to combine gravitational physics with quantum mechanics or the standard model. Now string theory string theory is very different from so string theory is not a theory that is proven. It's really a theory. And this is, I think, why we call it the standard model and not the standard theory. Because the standard model, as we understand it right now, is really it agrees with lots of experiments. There's no experiment that has been ever done to test string theory. So string theory is a mathematical construct which does allow to combine quantum mechanics and gravity together. But it could just be wrong. Okay, so we just don't know. We have never tested it. So it really is a theory in that sense, as in like it exists in our mind. It's a beautiful way of combining two things that seem very contradictory, but we don't know if it's correct or not. Oh, and there. Any internships? That is an interesting. I can look at that. Thanks, Sally. There's a question about internships that I would have to look into. So we certainly have lots of internships for undergraduates at the university. I don't know what exists for high school students, but I do know that there are several outreach. So I don't know the answer to the question, but I can certainly find out. And I will email, I guess, Alessandra or Anushka, who I had conversations with. If I find anything, I'll ask them, and I will communicate with them. And so let me write it down. Are there? So, so is the question? Would you like to do? Like, I guess Rishi asked the question. So you're looking for to do some kind of little project, some small research project. Is that what the question is about? Oh, so yeah, these are all direct messages. Okay, I'll just write it down. Other internship, possibilities. Very good. So, okay, this question here, string theory. So tell me when I should just stop reading. Well, I guess if you guys keep asking questions, I keep answering them. That just means that you're still interested. Is string theory really relies on dimensions above the third dimension? How will it ever be experimented? In principle, you can detect extra dimensions. So, for example, you could imagine that that you have a fifth dimension, and somehow the way you would see it is that maybe I shoot light somewhere, and so all of a sudden the light disappears. It just is gone. But maybe there is sort of an extra dimension sort of loops around in some way. So there is sort of people have theorized that you could actually see sort of light kind of appearing, disappearing, appearing, 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 and what really is happening that this light is traveling through some extra dimension. So you can certainly come up with predictions of extra dimensional theories, and people have made dimensions. And really, maybe the most striking prediction of extra dimensions is actually all these Newton's laws that you learn about. How, for example, two masses attract each other. They actually depend crucially on how many dimensions there are. So if you change the number of dimensions, Newton's laws will change. And so clearly we know that there's no fifth dimension at planetary sizes, because kind of Kepler's laws kind of work, right? But we have, for a long time, even like 20 years ago, people made a prediction that it is possible that if you take like some torsion balance and you put two massive objects really, really close together, that you actually start to see violations of Newton's laws. And that could be because there is literally 20, when I was a student in Toronto, it was still possible that there's extra dimension of the size of a millimeter that could exist. And those were then ruled out by literally measuring gravitational forces. So nobody ever actually tested if gravity is valid, if two objects are just a millimeter apart. Nobody had done that measurement. Now, of course, as soon as a theorist made that prediction, people went out and did the measurement, and they proved the theory was just wrong. So it was just an incorrect theory, but it was at the time possible. Okay, lots of people, internships, very good. I will have to look at that. Neutrino oscillations. So neutrino oscillations is essentially because neutrinos have mass. A little too complicated to explain, but essentially what you can show that if neutrinos have mass, then sort of the ways they interact with the weak force. How do I explain this? Is a good analogy that I can do? No, I can't think of something, but essentially what you can just work out the math, if you just write down neutrinos in the standard model and you give them some mass, then you just literally find, if you compute that, a neutrino can sort of, an electron neutrino can turn into a muon neutrino and back. And it sort of oscillates back and forth between these two things. And I don't have a good analogy right now to sort of explain why that is happening, but it's sort of a pretty straightforward math outcome if you write the equations down. And that is, so essentially neutrino oscillations have proven definitively that neutrinos do have mass. And as I just told you, we know that the standard model predicts that they do not interact with the Higgs boson. So neutrino oscillations are, and again, a direct conflict with the standard model. Now there it's pretty easy. It's actually very easy to think of an extension of the standard model that could explain that. But that is also an explanation of this, another indication that something the standard model is not exactly right. I think I have all the questions that are right now here. Feel free.
I have.
Yeah.
Does the Higgs boson have mass?
It does. Remember, I showed you this thing is 125 GeV. So now if you think that through, that actually means the Higgs boson interacts with itself, right? Otherwise it wouldn't have mass. So that is absolutely right. So if you actually look at, there's an interaction of a Higgs boson can turn into two Higgs bosons. And so one of the things, you can ask, well, at the Large Hadron Collider, we've now seen the Higgs boson. Why are we still running the Large Hadron Collider? There's many things that we haven't detected. So really, we've only measured the coupling of the Higgs boson to a couple of particles. So what we really want to understand is it really true that the coupling, so essentially what the standard model predicts is the coupling of the Higgs boson is proportional to its mass. That is where mass generation comes from. So we'd like to measure the coupling of Higgs boson to many more particles and check that relation, that is really true. And as we just said, the standard model makes a definite prediction the Higgs boson couples to itself. We've never seen that interaction. And so that is something else we'd actually like to see. So it's really, so at the moment, it's really, we've seen things that are consistent with the Higgs boson, but there's still actually many possibilities that the part of the standard model that gives mass could still be something that is not the Higgs boson, or multiple Higgs bosons, or just a completely different process. Any other questions? Very good. So does anybody remember how I save the chat? It might be useful to save the chat. Anybody remember how to do this? Before, because I know if I quit Zoom, the chat is gone, right? File. There's file. Here it is. Your computer. Let me put it onto my computer. Let me put it on my desktop, and then I can hand it to you guys. Maybe you guys want to see the. Where's my desktop? Desktop. Here it is. Okay. Desktop. Whatever. Okay. Oh no. Okay. Whatever. Sorry. Cancel. What is it? Oh, what is this? Oh no, this is uploading a file. Sorry, that's not what I want. I want to save it. Save chat. Here you go. Good. I think it's saved.
Cool.
I don't know where it got saved. Maybe it got saved to your cloud.
Thank you for coming. If you guys have more questions, just like email us and we can forward them.
Of course. No problem. Very good. Thanks so much. I had a lot of fun.
Yeah, thank you so much.
And I hope you guys can go back. Do you have any idea of when you guys will be back for real in real school? Will it be this semester? Because I guess high school is also not the first thing that goes back, right?
Right. It's likely gonna be next year, just because they want to get the younger kids in first.
Wow. So a whole year, 1.5 years of no. Geez.
Right.
Is it working for you guys? Do you guys see the teacher, or do you guys get reasonable, a reasonable education, you feel, or does it work?
It's definitely been harder personally than normal school, but it's not horrible.
Yeah, and I have it. My son, he's 8, so he started when he's like in first grade, and so it's it's okay. So now they're actually back. So he's in a private school, we kind of wanted to put him in public school, but now that COVID is hit, we're kind of happy that because he's been back for since November or something in school. It makes a huge difference, especially for the young kids, right? Who they just can't focus on Zoom for hours on end. I mean, it's hard for me to sit in front of a computer the whole time. So good. Well, thanks so much, guys. It was a pleasure talking to you.
Thank you so much.
Thank you.
All right. Bye.
Bye.
Bye-bye.